Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is focused on evaluating trigonometric functions of non-acute special angles. So up to this point, you should have watched my videos on, reference angles, arc length, right triangle trigonometry. All that will be very important. And the last video that I did was about unit circle and the unit circle approach to trigonometry. All of that is going to be critical here. And I'm taking a moment to also just talk about or recall what a reference angle is. So let's go ahead and do that right now. Recall that a reference angle is when you're given an angle and it is the smallest measure of, or it's a measure of the smallest positive acute angle formed by the terminal side of theta and the horizontal axis. And just to remind you again, it would look something like this. So if somebody said I had an angle that was 210 degrees, let's just pretend this is 210 degrees. Well, we know we've gone beyond the x-axis, right? We've circled all the way around to the x-axis, the negative x-axis here, and we've gone a little bit more, and it's that little bit more that we're interested in. That is called the reference angle. So if our angle is labeled theta, it is tradition to use theta hat as the reference angle notation. And we would not call, let's just say that was 210 degrees right there. So we went 180 plus an additional 30 degrees. Even though we're rotating technically upwards to go from this terminal side to the x-axis, since we're rotating clockwise, normally we would call that angle negative, but reference angles are never considered negative. They're always considered positive. It's just basically what's the fastest way to get to the x-axis, make sure that angle is just stated as positive. And I make that note here. Reference angles are always considered to be positive, even if they open clockwise. And here is where I start my mantra. So evaluation of trigonometric functions for non-axial angles. And what I mean by non-axial angles are that the angles don't land on an axis. So I'll write that up above. There we go. That's not very mathematical, by the way. I should say angles that do not terminate on an axis, but that's okay. Anyway, so evaluation of trig functions boils down to two things: reference angles and quadrants. And when I mentioned reference angles in my reference angle video, I had said these things are going to be incredibly important as we move forward. And here's where it happens. So let's see how this works. Evaluate all the trig functions for an arc length of t equals 5 pi over 6 along the unit circle. Now, just as we did in the previous video, we'll go ahead and shade an angle here, or an arc length of 5 pi over 6. And remember, on a unit circle, the arc length is actually equal to the angle that your arc subtends. And so that would be also in radians. So just to let you know, it's the angle in radians that your arc length subtends. So I'll go ahead and start showcasing an arc that opens up. Now remember, we're going to 5 pi over 6. And if the arc length for a unit circle is equivalent to the angle for the unit circle, then we know that all the way over here is an angle of pi radians. And pi is the same thing as 6 pi over 6 radians. And we're not getting exactly to 6 pi over 6, so we're a little bit shy of 6 pi over 6. So that would be the arc that we would shade, and we want to know what are all the trigonometric functions for that arc length, for that terminal point there. So let me plot the terminal point right here. We know that that shaded length is a length of 5 pi over 6, and therefore the angle that got cut out so that we end up at this terminal point right there, this angle is also an angle of 5 pi over 6 radians. Again, unit circles are very nice like that, and that's why some people really like the unit circle. Now what I'm going to state here is that we need to really worry about the reference angle. So what didn't we finish carving out? What's the fastest way to the x-axis? Well, this little angle right here is what we'll call theta hat. It's the reference angle, the fastest way to the x-axis. And note that we've only gone 5 pi out of 6 of the 6 pi out of 6 that would have gotten us all the way to that x-axis. So therefore, that reference angle must be the remaining little 1 pi over 6. And the reason why I say trigonometry is all about reference angles and quadrants is because this allows me to draw in a right triangle right here. And I can find the ratios of that right triangle. And if I find the ratios, the side lengths of that right triangle, then I will know what the x value is for it, and I'll know what the y value is for it. And then I can answer the question of what are all the trig functions at that arc length or at that angle. So let's go ahead and draw out our right triangle, pi over 6, pi over 3 right angle. First thing I want to draw your attention to here is that the way that I draw this is always going to be the same because I have a habit of drawing it where the smallest angle is up at the top here. So even though the orientation in this picture for this green right triangle, the pi over 6 is actually the right vertex, I generally just don't draw it that way when I draw it out outside of the unit circle. It's just a habit of mine. I also know that if the side opposite pi over 6, I often write as 1, and then the hypotenuse would be 2, and then the other leg would be root 3. Of course, we're in a unit circle, so that hypotenuse, which is this piece right here, that hypotenuse is of length 1. So I need to divide everything by 2. So I'll divide this by 2, that by 2, and this by 2, and you get the ratios that you need. So these are the side lengths if that was a triangle just sitting out in space, not in a coordinate system, but just sitting out in the world. You see a triangle, the side length or hypotenuse length 1, side length opposite pi over 6 being 1/2, and side length opposite pi over 3 radians being root 3 over 2. Now we have to consider the quadrant that we're in. So we use the reference angle here. Now let's consider the quadrant. You're in quadrant 2, so the x value there should be negative. And notice the x value is actually opposite the pi over 3 angle. So we'll go ahead and find out what is opposite the pi over 3 in our special triangle. Oh, it's root 3 over 2. So x must be a negative, because you're in quadrant 2, a negative root 3 over 2. And the y value, again, because you're in quadrant 2, must be a positive 1/2. And that is from our special triangle. So I don't need to do any other computations. I can actually just refer to my special triangle when I have a lot of different special angles. Notice this angle that I've been given, which is 5 pi over 6, that, even though it's called an arc length, it's also the angle. That angle that we've been handed is greater than 90 degrees. So we could not normally do what we're doing with right triangle trigonometry up to this point. However, because we know what the reference angle is, pi over 6, we could draw a right triangle and pi over 6 will fit nicely in there, and we can find the trig ratios from that. So now I can just say, great, that point, that terminal point right here, whoops, except I need a good highlighter for that. That terminal point right there has an x value of negative root 3 over 2 and a y value of 1/2. Now I can state all the trig ratios. The sine of that 5 pi over 6 is going to be the y value. The cosine, again, of that 5 pi over 6 is going to be the x value, negative root 3 over 2. The tangent, again, of 5 pi over 6 is the y value over the x value, so 1/2 over negative root 3 over 2. Multiply both top and bottom by 2, and you'll get a negative 1 over root 3. And then the other three are just the reciprocals, right? So cosecant of 5 pi over 6 will be 2. The secant, and I have to fix that. The secant of 5 pi over 6 will be negative 2 over root 3. Again, I don't reduce or rationalize denominators. And finally, cotangent of 5 pi over 6 is a negative root 3. All just from using my special triangle, my 30, 60, 90 triangle and right triangle trigonometry. And here I have forgotten to put this theorem into my lecture notes, and so I quickly have just scratched this out. But this is like one of the most important theorems. I don't know why this just got left out of my typed lecture notes, so I'll have to type that in later on. But the value of a trigonometric function at an angle theta is the same as the value of the trigonometric function at its reference angle theta hat, with the exception of the SIGN sign, the plus or minus sign. That can be determined by the quadrant. So let's go ahead and think about this. I give you some angle theta. Okay, let's pretend that it lands us all the way over here. There's our angle theta right there. Okay. And notice the terminal side of theta has a point, x, comma, y. Right. Now, our reference angle, theta hat, builds for us a triangle, a right triangle, in fact. And so we can, that's a terrible looking picture. Let me actually clean that up. Except I didn't want to erase the x-axis. There we go. So we can build a right triangle right there. And this angle right here is theta hat. Great. So let's go ahead and take a look at that right triangle that we've just drawn. I'm drawing it in green. Let's zoom into that. And when I say zoom in, I mean really what I'm going to do is just redraw it out here larger. So we have this right triangle. We have some, we have this theta hat right here. We have some adjacent side, we have an opposite side, and we have a hypotenuse, right? So we have all three of those things. We don't have them, but let's just pretend as though we can find them. Then the sine, for example, of theta hat, well, we know that's going to be opposite over hypotenuse. Now this triangle is sitting out in space. All of these values for this triangle are positive. They're greater than 0 because it's just a triangle sitting out in space. All these values would be positive. And the side lengths and hypotenuse length of a triangle out in the real world, they're all positive lengths. The cosine of theta hat would be adjacent over hypotenuse. You get the whole idea. You would just find their ratios using right triangle trigonometry. However, those are all going to be positive values. Now think about this. With the sine here being opposite over hypotenuse, while the numbers, their absolute values, are actually matching here, this is actually the opposite, the negative opposite of the opposite. And this is because x values are positive here. That is actually the value of the adjacent, and this is actually the value of the hypotenuse. But the y value is negative, so it's not going to be the same as the right triangle trig opposite side. It's going to be the negative of that. So the sine of, let me draw this in black, the sine of theta will not be opposite over hypotenuse from our triangle, because the sine in quadrant 4 is negative. And so it's going to be negative opposite over hypotenuse. But otherwise, the ratios hold. So what you do is you draw your right triangle outside of your axes there, and then you just take into consideration what quadrant you're in. So if we're in quadrant 4 here, I happen to know the sine should be negative. So rather than writing opposite over hypotenuse, I would say it's the negative of opposite over hypotenuse. Cosine of theta, well, again, we're in quadrant 4. Cosine is positive in quadrant 4, so that's adjacent over hypotenuse. There's no need to throw an opposite on there. Tangent of theta. Now we know if we were just dealing with right triangle trigonometry, the tangent of theta hat would be opposite over adjacent. The tangent of theta, because we are in quadrant 4, is negative, and then opposite over adjacent. Oops, ADJ. So the ratios for the reference angle are kind of the base, what you're starting to work with, and then you take into consideration the quadrant to put the plus or minus signs on your trig functions. So this will make our computation for unit circle trigonometry incredibly easy and familiar, because it's going to be the same as right triangle trigonometry. So notice, for example, in this example 5 that we did here, we could have, instead of drawing the triangle right here, we could have just said, okay, we have 5 pi over 6. Our reference angle is pi over 6. So I could have made that note that this reference angle is pi over 6, and then do what we did over here. We drew out our triangle with the reference angle of pi over 6, and then found the ratios of the sides and said, okay, so without even looking, other than the fact that knowing that we're in quadrant 2, without looking at our unit circle, I would say, okay, our reference angle is 5 pi, or pi over 6. So sine of 5 pi over 6 is almost the same as sine of regular old reference angle of pi over 6. We just have to worry about the quadrant. Well, that's a quadrant 2 angle. Sine is positive in quadrant 2. Let me actually write that in a different color. It's positive in quadrant 2. And cosine of 5 pi over 6, without looking and worrying about anything else, I'll just say, well, that's quadrant 2, 5 pi over 6 is. So this should be, cosine is negative in quadrant 2, so it should be the negative cosine of pi over 6. And tangent of 5 pi over 6. Well, again, we are in quadrant 2, and the only two trig functions that are positive in quadrant 2 are sine and cosecant. So tangent will be negative in quadrant 2, and it'll be the negative tangent of the reference angle, pi over 6. And then I can go ahead and just use my right triangle trigonometry, and I don't even have to actually solve that. I could use my standard right triangle if I want to. This is the one I like to use, 1, 2, root 3. And I can say, okay, the sine of pi over 6, opposite over hypotenuse, 1/2. Great. And let's see, cosine of pi over 6, that's adjacent over hypotenuse, root 3 over 2. But it's negative, remember, so it's a negative, and then root 3 over 2. And finally, the tangent of pi over 6. Tangent is opposite over adjacent, 1 over root 3, but again, in quadrant 2, it's negative, so negative, and then 1 over root 3. Now, if you look at our actual trig ratios, you'll see right here, they're the same numbers. So it's a really nice way to do it. And that's the way I'm going to do it from this point forward. So I'm going to ask, what's the reference angle and what quadrant do we land in? Let's actually do that. Evaluate all trigonometric functions for the arc length of t equals negative 3 pi over 4 along the unit circle. I really don't care that the angle here is negative. I just want to know, and I'm going to chicken scratch this out. So in other words, I'm not going to bother with my beautiful drawings there. I'm just going to open up an angle that goes here's, remember, if we went all the way backwards here, that'd be a negative pi as the angle. But negative pi is the same thing as negative 4 pi over 4. Notice I keep putting things in terms of the denominator of the angle that we're given in radians. So that's important. So we didn't go all the way to negative 4 pi over 4. We went to negative 3 pi over 4. So this is negative 3 pi over 4. T equals a negative 3 pi over 4. So our reference angle, which I'll call, technically, this should be a theta. Our reference angle we'll call theta hat. And our reference angle here is just an additional little pi over 4 that we would have gone. It's not going to be negative. I totally get that you're going to say, but wait, it's a negative pi over 4 because negative 3 pi over 4 plus a negative pi over 4 gets me to negative 4 pi over 4. You're right. But reference angles are always going to be called positive. So it's a positive pi over 4. So now what I'm going to do is draw a right triangle. I wouldn't normally not even draw it here, but I'm just showcasing it. I'm going to draw a right triangle off to the side here. But the right triangle I'm going to draw is going to have a pi over 4 as an angle. And that's a special triangle. Pi over 4 right angle. 1, 1, and root 2. So that's our special triangle. And now I can just use the reference angle, pi over 4, to go ahead and find the trig ratios. So let's go ahead and write out all the trig functions here. And I'll pause to do that. And take a look at those angles, right? Negative 3 pi over 4, all the angles. And we happen to know those angles are quadrant 3 angles. And we happen to know the reference angle is pi over 4. And again, just zooming out, trig functions, evaluating them boils down to two things: reference angles, which we just stated, and quadrant, which we just stated. Now what I'm going to do is go ahead and state in quadrant 3, which of those functions are negative and which of them are positive. Well, we know that in quadrant 3, the sine is negative, the cosine is negative, but the tangent is positive. So therefore, their reciprocals have the same behavior: negative, negative, and positive. Now let's go ahead and now just use the reference angles to evaluate these trig functions. So if I go up to our right triangle here, the sine is just opposite over hypotenuse, 1 over root 2. So it's going to be, don't forget the negative sign, negative, and then 1 over root 2. The cosine is going to be adjacent over hypotenuse. Again, a 1 over root 2. But again, don't forget the negative sign. It's a negative because we're in quadrant 3, 1 over root 2. Should probably make a little break here so we can see they're different. The tangent of pi over 4, well, that's opposite over adjacent, 1 over 1. So that is going to be, and remember, tangent's positive in quadrant 3. So that's just going to be a regular old 1. And now the reciprocals, I could just flip things over, right? So the reciprocal, the cosecant is going to be a negative root 2 because the sine is negative 1 over root 2. The secant is going to be a negative root 2 because, again, the cosine is a negative 1 over root 2. And then the cotangent is going to be 1 because the tangent's 1. So I filled all those out with barely even looking at the kind of unit circle approach. All I did for the unit circle approach was draw. I just want to know, where does that negative 3 pi over 4 land? And then once I'm done with that, I find the reference angle and the quadrant, and I'm ready to go. Now, 2 examples, it's just not enough. But before we do that, before we move past or into another example, I want to ask a question here that's kind of important. What would happen if we no longer considered the unit circle, but instead, what if we had a circle of radius 300 or something like that? What would happen to our entire conversation? Well, here we have a unit circle, and we know that the trig functions are defined via the unit circle definition to be in terms of the x and y value of that point right there. So the sine is the y value and the cosine is the x value. And of course, the radius or the hypotenuse length here is of length 1. And we could draw in, if we wanted to, a right triangle. And if we drew in that right triangle, we could figure out the leg lengths there. They're just x and y. Now, using that right triangle that you see as a template, if I just had that right triangle hanging out in space here, and I said, hey, I need to know what are the trig functions of that angle. Sorry that it's a little bit blocky. I made this kind of a small thing, but what are the trig functions of that angle theta? You would say sine of theta is just opposite over hypotenuse, y over 1. And cosine of theta is adjacent over hypotenuse, x over 1, and so on and so forth. So again, for this unit circle, which has this right triangle, we know that the, for example, sine of theta is y over 1. And we know the cosine of theta, I'll just scroll down a little bit, cosine of theta is x again over 1 if we looked at the right triangle. But remember, for a unit circle, sine of theta is defined to be y. But what if we weren't working with a unit circle, but instead we were working with a circle of radius, let's say 5? Well, how would things change? They wouldn't change too much, actually. We would have a different, obviously, x value here. So let me go ahead and draw that in. This is the x value. I'll call it x hat. Let me zoom in and make that a little bit cleaner here. So I'll call this, oops, didn't want to erase that. I'll call this length here on the x-axis, I'll call that x hat. And I'll call this height here y hat. But we know that the hypotenuse length is 5 because we multiplied the triangle by a size of 5, right? So, or by a value of 5. But it's the same dimensions. It just got exploded up. Okay. Now let me go ahead and draw that right triangle off to the side here. So here's our right triangle. Here's our angle theta. By the way, you should agree, the angle theta here is the same angle theta that we had in our red right triangle that we started with. So it should be the same exact ratios. This is y bar, this is x bar. So our new ratios, by the way, y bar will just be 5 times the original y value. X bar should be 5 times the original x value. So this should be 5y, this should be 5x. Now let's ask ourselves those same questions of what are the trig ratios? Well, the sine, if this triangle was hanging out in space, the sine would be, again, opposite over hypotenuse, 5y over 5, which is y. The cosine of theta would be the adjacent, 5x, over the hypotenuse, 5, which turns into x, which is exactly the same as what they would have been if we were in the unit circle. So what I'm trying to imply here is, doesn't matter actually how large the circle is. It turns out that if you increase the radius of the circle, the true definition, what I call the point definition for the trig functions, are the following. The sine of the angle is going to be the y value over the radius of the circle. The cosine of the angle is going to be the x value over the radius of the circle. The tangent of theta will be y over x. That doesn't change. And then the reciprocals are just the reciprocals, right? So the cosecant of theta is going to be the radius over y, and the secant of theta is going to be the radius over x, and finally the cotangent of theta is just going to be x over y. So if you are working with a unit circle, the radius is 1, and you get sine is y, cosine is x, cosecant is 1 over y, secant is 1 over x, so all the definitions hold. But if you increase the radius, well, then you have a larger radius to consider. The point definition, this one that I've kind of written down within an example, is not as common to use as the other definitions, which is unit circle and right triangle trig definitions, but it is helpful at times. In fact, when we get to the end of the course and we're dealing with polar coordinates, they are defined in terms of these definitions right here. So it is critical that we remember that the sine of theta, it is opposite over hypotenuse. It is also in a unit circle, y, but probably a better definition is in any circle, the sine of theta is y over the radius of the circle, and so on and so forth with all of the trig definitions there. So let's go ahead and use that new idea to find the coordinates of the point on a circle of radius 10 corresponding to an angle of 16 pi over 3. Now this will require both the use of reference angles and quadrants. That's going to be super awesome. What you're going to notice with trigonometry is you have options. And because you have options when you're dealing with a problem, it can be somewhat intimidating. You're juggling 3 definitions of trigonometric functions and trying to find the one that works best for you. Not for me, but for you. As long as you're right in the end, it doesn't really matter how you approach it. So the radius of the circle is 10. I happen to know that this will be 10, 0, and this will be 0, 10. I'm just drawing that in there because it's just nice to have that information. And we're rotating through an angle of 16 pi over 3. Well, let's see. This would be an angle of pi, which is the same thing as 3 pi over 3. So obviously getting to that point right there is not going to be enough. So if we continue to rotate, so let's just say I rotate around here and I get all the way to this point, I've gone 3 pi over 3 radians. Well, I continue. And now I'm over here at 2 pi, which is the same thing as 6 pi over 3 radians. And notice I'm not quite there. So I have to continue. I keep rotating. And I'm over here, I add another 3 pi over 3, so now we're at an angle of, let's see, 3 pi over 3, 6 pi over 3, this will be 9 pi over 3. So they're actually not the same angle, but whatever. And I keep rotating, because that's just not to 16 yet, so I keep rotating, I add another 3 pi over 3, so now I'm at 12 pi over 3. And that's just not good enough, so I keep going. And I keep rotating, I add another 3 pi over 3, so now I'm at 15 pi over 3. Let me write that in here if I have room. Oh, I do. 15 pi over 3. Now we're really close, right? 15 pi over 3 is really close to 16 pi over 3. So I'll just go a little bit more. Just a teeny little bit more, actually. And that teeny little bit more is an additional pi over 3. So theta hat, our reference angle, is an additional little pi over 3. Now that I know my reference angle, I'm going to go ahead and just go back over here and draw my 30, 60, 90 triangle like I always do with the pi over 6 at the upper vertex, just because it's a habit of mine. Pi over 6, pi over 3, 1, 2, root 3. Okay. And I would be able to read off all of the trig ratios just from this specific triangle. If you take a look at this circle, it doesn't have a radius of 1. And in fact, if you look at my triangle, our circle doesn't have that radius of 2 either. So what we can do is we can say, well, the radius here is actually 10. So I would like to explode this triangle here to have a hypotenuse of length 10. So you can multiply all three sides by 5 if you want to do that. That is one way to approach this problem. So I'm going to do it that way first. Maybe you like it, maybe you don't. If you don't, I'll do it a different way when we get to the end. So I'm going to multiply everything by 5 first, just to showcase that, we're exploding the size of this triangle. And when you multiply that everything by 5, you get that this is side length 10, this is side length 5, and this right here is side length 5 root 3. Great. And now I can just go ahead and list out all the trig functions, noting that we're in quadrant 2 or 3, and we have a reference angle of pi over 3. So again, we're in quadrant 3, and our reference angle is a pi over 3. That's going to be critical. So let me go ahead and write down all the trig functions here. And now we'll start considering the quadrant. Since we're in quadrant 3, I know the sine will be negative, the cosine will be negative, the tangent is positive in quadrant 3, and of course, therefore, the reciprocals, the cosecant's negative, the secant's negative, and the cotangent will be positive as well. All right, now let's go ahead and consider the actual trig functions evaluated at the reference angle, which is pi over 3. Let's look at our triangle up here. Pi over 3 is this angle right here. So let's see, the sine is opposite over hypotenuse, so that'll be 5 root 3 over 10. So a negative, let me write the negative in there, a negative, and then I'll write in the 5 root 3 over 10. And if you notice, that is going to be root 3 over 2, negative root 3 over 2. So let's go ahead and write that in. I'm going to loop this stuff up and move it so that we have the room. There we go. And so this is going to reduce down to, even though we're dealing with a larger circle, a negative root 3 over 2, which would have been what we would have gotten had we just left this alone and not exploded the triangle. The sine is, again, opposite over hypotenuse, root 3 over 2. And this goes back to what I just said a few moments ago in the previous page, that it turns out that no matter how large you make the triangle, the ratios will always be the same. So because we blew this triangle up to a size of 10 rather than being a unit circle, doesn't really change the trig ratios at all. And so now that I know that, I can go ahead and perform the rest of this problem with my standard triangle. There's no need for me to blow this triangle up. I get to use the same ratios throughout because the 5 over 5s always cancel, basically. That's from this picture right here. The 5 over the 5 cancel. So the cosine, now I'm just going to read right off of this. The cosine of pi over 3 is adjacent over hypotenuse, 1 over 2, and it's going to be negative because we're in quadrant 3, so it's a negative 1/2, negative, and then 1/2. The tangent is opposite over adjacent, root 3 over 1. So positive root 3 because tangent's positive in quadrant 3. And then we'll just take the reciprocals for the reciprocal functions. So the cosecant will be a negative 2 over root 3. The secant will be a negative 2, actually. And finally, the cotangent will be a positive 1 over root 3. So it turns out the radius of this circle plays no role in the values of the trig functions. And so now we can go forth and dominate the world with our trigonometry. Now you might have a question. You might be saying, like, wait a second, I thought that a few minutes ago you said that the sine was the y value divided by the radius. So I thought the radius or the size of the circle does play a role. It absolutely does. But when you explode the size of the circle, the y values will also explode accordingly. So if you multiply the radius by 5, like we did, the y values will multiply by 5 as well. So y over the radius, that 5 will cancel, and you'll get back down to your regular trig ratios of root 3s over 2s and 1/2 and stuff like that. The other thing I want to mention here is I gave you a very large angle. That's super common. So you have to be willing to say, you know what? These trig functions of 16 pi over 3 are kind of the same had I just not worked with 16 pi over 3, but instead had I unwound this a little bit and removed as much of the rotation as possible. So instead of rotating around 3 times or how many ever times we did, how is it, or is there a possibility that I could have, just trying to clean things up, is there a possibility that I could have just rotated directly into quadrant 3 without having to rotate 3 times around? And the answer is yes. If you're given a massively large angle, what really truly matters is where you end on your rotation. So I could rotate around this circle a billion times, but once I end there, well, that's all I truthfully needed was just a single little partial rotation to get there. I didn't need all the excess. So what you could do is, given an angle theta, you could start unwinding it by subtracting, my theta looks terrible. You start subtracting 2 pi's. And remember, 2 pi is the same thing as 6 pi over 3. So it's not that theta is going to equal 16 pi over 3 minus 6 pi over 3, but you can start stepping it down to 10 pi over 3. That's me losing 6 pi over 3 or a full rotation. And step it down again, losing another 6 pi over 3 to 4 pi over 3. I have unwound this a couple times until I get to an angle that's less than 2 pi, and then I can evaluate the trig functions at that angle instead. So again, this is actually a theorem, but we're not going to label it as a theorem yet. But it turns out that sine of theta is the same thing as sine of theta plus any integer rotation of 2 pi, where k is an element of the integers. That's going to be a theorem that we'll write in the future, but the reality is that the sine of, let's say 150 degrees is the same thing as the sine of 150 degrees plus 360 degrees. So as long as you end at the same terminal point, you could rotate a billion times and then add that extra 4 pi over 3 to land there. And the same thing for all the trig functions, by the way. The cosine of theta is the same thing as the cosine of theta plus any rotation of 2 pi. And tangent, the same thing. So this can be very useful to unwind those rotations. Tangent's a little more special, actually, but we'll deal with that later. So here's a good example of that. Evaluate all trigonometric functions for the angle negative 2010 degrees. That's a ridiculous angle. So what I'd like to do is start adding 360 degrees to kind of get this back to something even positive would be nice. So if you add 360, that will not get us to a positive angle. Not that you need to get to a positive angle, but you want to add 360 at least enough to where you make this angle smaller. So I just start rotating and rotating and rotating and rotating. And let's see, that's about 1400 or so. So I'm going to add maybe one more of these. What's that? 5 times 3 is 1500. 6 times 3 is another 3. That's 1800. Still not enough. I'm going to add another 360. Let's see. 6 times 3 is 1800. And 6 times 6 is 360. So that's 1800 plus 360 is enough. If you add all these up to negative 2010 degrees, you'll get to 150 degrees. So really this angle that we're dealing with is going to land us in quadrant 2 at 150 degrees. All said and done. So there we go. It's a 150 degree angle. I'll call that theta. Now, even though that's not theta, maybe I shouldn't have called that theta. I'll call it theta sub 1 because they labeled theta as negative 2010 degrees. So labeling it something different, it's kind of nice. But again, trig is all about reference angles and quadrants. So what quadrant are we in? Quadrant 2. And what's our reference angle? Our reference angle is 30 degrees. So now I just need to draw my 30, 60, 90 triangle. And I'm in degrees, so that's nice. I think familiarity is always nice every once in a while. I shouldn't say always and every once in a while. I should say it's nice every once in a while. 30, 60, 90. 1, 2, root 3. And now I could just write out all of my trig functions here. Let's go ahead and write them right here. And this time I'm just going to go ahead and stop with the sine, cosine, and tangent. I won't write the reciprocals because you get kind of tired of doing that. Let's see, our reference angle is 30 degrees, so let me go ahead and do that. We're also in quadrant 2. So in quadrant 2, all students take calculus, right? All students take calculus. So in quadrant 2, the sine is going to be the only one that's positive of those 3. So I'll write the positive here. And the other 2 will be negative. And again, our reference angle was 30 degrees. So this will be the same thing as a positive sine of 30 degrees. And this down here will be the same as a negative cosine of 30 degrees because we're in quadrant 2, cosine is negative. And the negative tangent of 30 degrees, again, because we landed in quadrant 2, tangent will be negative. And we can just go to our right triangle over here. The sine of 30 degrees is opposite 30 over hypotenuse, or 1/2. The cosine of 30 degrees is adjacent to 30 over hypotenuse, root 3 over 2 with a negative. So negative root 3 over 2, I'll just drop the color, negative root 3 over 2. And then the tangent is opposite over adjacent, 1 over root 3, negative. So you should start seeing that, wow, you can really deal with an infinite number of trigonometric functions by hand. You don't need a calculator for these. All these you can do by hand. And that's critical. If you're in a trig course, you want to do as much by hand as possible because trig takes kind of this touch. You have to be able to touch trig to work with trig. Again, reference angles and quadrants. That's what trig is all about. Compute this product. So now we're dealing with actual they didn't say like, oh, what's the cosine or sine or tangent of 5 pi over 6? Instead, they're like, what's this product? Cosine of 5 pi over 6 times the cosine of 2 pi over 3. Well, this will require us to draw out 2 different pictures. One for an angle of 5 pi over 6, which is almost all the way over to 6 pi over 6, which is pi. We have a reference angle here of pi over 6. We are in quadrant 2. Again, trig is all about reference angles and quadrants. The other picture, maybe I should draw that one in blue actually. So let me erase this and draw that in blue. The other picture goes to angle of 2 pi over 3. Well, again, pi is 3 pi over 3. So we're almost all the way over to pi, but we're only to 2 pi over 3. We're just shy by a single little pi over 3. That's our reference angle. That's our theta hat here, if that's theta. And since I'm using the angle theta for the blue ink, I'll use the angle alpha for the black ink just to keep everything legit. There we go. All right. So we have 2 triangles we have to deal with. Luckily, they're the same triangle, actually. So the 30, 60, 90 triangle, except I always write as pi over 6 up here and pi over 3 down there, and 1, 2, root 3. So the cosine of 5 pi over 6 is going to be almost like the cosine of regular old pi over 6. It's reference angle, except we're in quadrant 2. And remember, all students take calculus. Cosine is positive in quadrants 4, and everything is positive in quadrant 1. So in quadrant 2, which both of these angles actually terminate in, cosine will be negative. So let's go ahead and trade out the cosine of 5 pi over 6 and the cosine of 2 pi over 3 for two different values. The cosine in quadrant 2 is negative. Cosine in quadrant 2 is negative. And our 5 pi over 6 has a reference angle of pi over 6. So this would be the cosine of pi over 6. And our 2 pi over 3 has a reference angle of pi over 3. So this would be cosine of pi over 3. Negative times negative is positive, so the negativity goes away. And then I just use my right triangle above for the rest of it. The cosine of pi over 6 is root 3 over 2. The negative's canceled, so I'm not writing the negative now. And the cosine of pi over 3, adjacent of our hypotenuse, is 1 over 2. This is root 3 over 4. So notice how I'm constantly using right triangles. I like right triangle trigonometry so much. And you notice that I rarely reference the unit circle anymore. And it's because right triangle trig really dominates most of your mathematics. Now, something I want to mention, if this is your first time seeing trig, and it probably should be your first time seeing trig, I just want to mention a mistake. So this is a bit of a warning, because I know that every once in a while students will do this. It's really weird that they do this, but it's just important to note. If you have, let's say, a cosine of A times a cosine of B, that is not equal to the cosine of A times B. You can't glue together their arguments. That just doesn't work out. These are two completely different functions multiplying, and you follow the order of operations, really. You clean up A and then evaluate cosine at A. You clean up B, evaluate cosine at B. Then you multiply those two together. That's the order of operations. Also, I should note the cosine, and when I say cosine, I mean any trig function. It could be tangent, cosine, sine, cosecant, secant, or cotangent. Any of them. These are all things that are untrue about them. So cosine of A plus cosine of B is definitely not the cosine of A plus B. So again, these are completely different functions. You have to evaluate them first. Clean up A, evaluate cosine of A. Clean up B, evaluate cosine of B, and then add them. Right? So you cannot just add the A and B. That just doesn't happen. So be very careful about that. I know a lot of students who have done that in the past, so I tend to want to make sure that they don't make that mistake again. We're finally nearing the end here. I know this is a long video. It's only because you're learning a lot in this video, learning how to really compute. And so now we're to the end where we're just using technology to compute trig function values. And we've done this before, but we've only done it for acute angles. And now we're dealing with non-acute angles. In other words, angles greater than 90 degrees and or greater than pi over 2. So how would you compute these? Very simply, just use a calculator. So here I am over in Desmos, and I'm in degree mode. I know that I'm in degree mode because degree mode is highlighted. And you can easily check that because you should be able to know that the sine of, for example, 30 degrees is a half. And if it doesn't respond with a half, you know you're in radian mode. So anyhow, now that I know that I'm in degree mode, we had one question that asked, what is the cotangent of 137 degrees? Well, the cotangent of 137 degrees is the same thing as 1 over the tangent. You cannot just plug in the cotangent to most calculators. So you have to use the reciprocal identity. Cotangent is 1 over the tangent. And then you can type in 137. That is assumed to be degrees because we're in degree mode. So you do have to be very, very careful about that you are in the proper mode. So this is roughly a negative 1.07. And then I'm going to clear this because if I don't, once I switch to degree mode, it's going to, or radian mode, it's going to change that. So I'll clear it. And now the other question was in radians. It was actually hidden. It asked, what's the sign of negative 3? That negative 3 didn't have degrees. And so if it doesn't have degrees, that means you're dealing with radians. So I'm going to put in radian mode and then type in -3, and it gives me approximately, again, very approximately, let's see, a -0.14. And you can see I wrote these here. Again, note what we were handed. The sign is not -3 degrees, it's just -3, which means it's radians. And the cotangent with the degree sign, yes, definitely the cotangent of 137 degrees, but most calculators do not have a cotangent button, so we had to trade that out for a 1/tangent of 137 degrees. And we found that to be roughly -1.07, and the sign of -3 radians, roughly -0.14. This final image here is really just for your benefit. Some people love the unit circle. I really don't understand why. I know there are patterns with it, but it is honestly more of a memorizable piece, and I think that's why students love it, because they like to memorize. But really, all of these, look how busy that is. I can give you all the same information with 2 triangles. I can give you all the same exact information, except for at the axes, which we'll do in a different video. But I can give you all the same information with a pi/4. Oh, it's a terrible pi/4. Let me do it this way. I give you the same information with my pi/4 right angle, 1/√2, and with my pi/6 pi/3 right angle triangle, 1, 2√3. You land anywhere on that triangle that's not on an axis, because I'll talk about that in the next video. But if you land anywhere, let's say you're like, oh man, I've got a terminal point at 5 pi/3, and I need to know those values. I would say, oh, 5 pi/3, the reference angle is pi/3. Great. So let me look at my pi/3. The sign of pi/3 would be √3/2. However, you're in quadrant 4, so it's a -√3/2. Let's see what they say the y value is. Oh, look, a -√3/2, right? So I could rebuild this whole thing very quickly if I want to, using my right triangle trigonometry. I don't need to memorize this whole stupid table or this whole stupid picture. And like I said, we'll deal with the axial angles, the 0, 90 degrees, 180 degrees, 360 degrees, 270 degrees. We'll deal with that in the next video. This video's super long. Sorry about that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.